Well, I'm certainly very much honored by this occasion. I'm very happy to be here at the University of Oslo. If I remember correctly, it was 26 years ago that I previously gave a lecture here, so it's wonderful to be back. So I have to, first of all, introduce the subject that I want to talk about. So I'm talking about spheres. So the the standard example of spheres, the round sphere in any dimension, is defined as follows. To look at the n-dimensional sphere, you start with the n+1 dimensional Euclidean space, and then look at all points which have distance exactly 1 from the origin. So that's given by that simple equation. Now, here's the one-dimensional example, the one-dimensional standard sphere. It's a beautifully symmetric, smooth object. But I also want to look at objects which are much rougher. So this is an example of a topological one-sphere. So when we say it's a sphere or topological sphere, I mean that you can parameterize the points of this wiggly object by the points of the standard sphere. So each point of the lower picture can be labeled by a point of the upper picture such that nearby points have nearby labels, and distinct points always have distinct labels. But I also want to study smooth objects which are spheres in the sense of topology. So this is an example of a one-dimensional object, which again is a topological sphere. It can be parameterized by the standard sphere, but in this case the parameterization is completely smooth, so it has a derivative, and its inverse has a derivative. So these are the kinds of objects I want to look at, but of course the one-dimensional case is not very interesting. I'm showing you the one-dimensional case to give you an idea of what I'm talking about, and because it's very hard to draw pictures in high dimensions. But I can at least give you some two-dimensional examples. Here's the two-dimensional standard sphere, and there's a two-dimensional topological sphere, and here's a two-dimensional smooth sphere. I should give you some credit here. This is a very high-tech picture, space photograph taken from a Japanese space probe. And this is a very low-tech object carved by a lady in northern Canada. But, well, that's about as far as I can go with pictures. It's pretty hard to draw a picture of a three-dimensional manifold, except for the three-dimensional Euclidean space, which we live in. So let me go on to study the problem. That picture doesn't seem to come out very well. Well, I'm sorry. So this is intended to be a picture of Poincaré. I don't know what happened. So this is a question which Poincaré asked in 1904. Est-il possible que le groupe fondamental devait survivre de substitution identique et que pourtant they ne soient pas simplement connexes? Now, this is, beside from the fact that it's in French, its mathematical terminology has changed in 100 years. So that's one problem, that the word simply connected means something very different today from what Poincaré meant by it. And also, of course, I've taken this out of context. He was talking about three-dimensional manifolds, so it's understood here that V is to be a three-dimensional sphere. And his question was, if the fundamental group of V is trivial, does it follow that V is isomorphic to the simplest possible example, in this case to the standard three-dimensional sphere? Well, that was more than 100 years ago, and it took about 100 years for the problem to be solved. But on the way, there was a great deal of thought. The first 50 years after Poincaré's question was mainly occupied by discovering how difficult it was, because there were many, many attempts to prove the Poincaré conjecture, and none of them worked. There were many different ideas which almost seemed to work. We reduced it to a simpler question, which you also couldn't solve. And then about 50 years ago, it began to be realized that dimension 3 was particularly difficult. And if you go to higher dimension, the analogous question becomes much easier. So this we refer to as the generalized Poincaré hypothesis. And 100 years later, we found this answer, the theorem, the generalized Poincaré hypothesis theorem. A closed n-dimensional manifold is homeomorphic to a sphere if and only if it has the same homotopy type as a sphere. Or if you don't know what homotopy type is, here's a simpler description. It's a manifold that is locally, it looks like Euclidean space near any point, and yet any proper subset can be shrunk to a point completely within the manifold. So if you take a two-dimensional sphere in any proper subset, say missing the North Pole, then you can just push it down to the South Pole, and similarly in any dimension. So that's the theorem, and it's certainly not the work of one person. It's a compilation of work by many different people. And when I say 150 years now, it's because the low-dimensional cases were known even before Poincaré. So in dimension 1, it's quite easy. Dimension 2 is rather difficult. If you don't know a proof and sit down and try and prove it, I think even today you'll find you have your hands full. So I've given a reference to a modern paper which describes a proof in the two-dimensional case. Well, but the big breakthrough some 50 years ago was this discovery that higher dimensions really are easier. And the first person to make a breakthrough here was Stephen Smale, who first proved it in higher dimensions and then managed to push the proof down until it worked even in dimension 5. But he didn't quite prove the full theorem. What he proved finally was a topological result, that a manifold was homeomorphic to the standard sphere in that dimension, but he had to assume that the thing he started with was a smooth manifold. And shortly afterwards, John Stallings gave a proof which made a weaker assumption, only that it had a manifold with a good triangulation and was sufficiently high dimension. Then Chris Seaman managed to modify Stallings' argument so it worked again down to dimension 5. But still you couldn't handle an arbitrary manifold. You needed a good triangulation to start with. And then finally, a few years later, the two people independently proved that the Stallings argument could be modified so that it would work with an arbitrary topological manifold. So Max Newman and Ed Cannell. So this meant that the topological generalized Poincaré hypothesis had been proved in all dimensions greater than 4. But there were two stubborn cases left over, the three-dimensional case, the original one which Poincaré had asked, and the four-dimensional case. So the four-dimensional case was the first one to fall. And this was some amazing work by Mike Friedman. And it was very definitely not a smooth proof. It used very wild topological constructions in order to prove the four-dimensional theorem. And in fact, he proved much more. He gave a classification of all closed, simply connected four-dimensional manifolds. And he showed that they were totally classified by just two simple invariants. One was an algebraic invariant, the quadratic form, where if X varies over the middle cohomology group of the manifold, which is just a free abelian group of some rank, then the cup product of X with itself belongs to the top dimensional cohomology, which is, given an orientation, we can identify with the integers. So this is a quadratic map from a free abelian group to the integers, what we describe as a quadratic form. And then there was just one other invariant, just a number modulo 2, which, well, it vanishes if and only if the product of M with, say, a line can be given a smooth structure. So it's a kind of obstruction to smoothness. So it's rather surprising that the original question was invention 3, and at this point, we've been able to solve every other case except for the question he'd actually asked. And just a comment, I wrote cohomology here without mentioning the coefficient group. In fact, I'll always talk about cohomology or homology with the integer coefficients in it, so I won't bother to use a separate notation for it. Okay, so the hardest case, n equals 3. The first big step was by Bill Thurston, who provided a very powerful conjecture suggesting how to that every three-dimensional manifold could be put together, cut up and, into simple pieces, each of which had a beautiful geometric structure. So the conjecture not only included the original Poincare hypothesis, but it gave a complete picture of how to understand all possible three-dimensional manifolds. And he proved this theorem and this conjecture in many interesting cases. But his work certainly couldn't handle the original case of the Poincare hypothesis. So the next step was by Richard Hamilton, who suggested a method, a possible method for proving this geometrization conjecture, and in particular for proving the Poincare hypothesis. It involved a differential equation, a kind of heat flow type equation in which you start with a smoothly curved manifold and then let the curvature gradually change so that the points of very high curvature, the curvature decreases, points of low curvature, the curvature increases to try to get it to smooth out, excuse me, smooth out into a uniform curvature. And he was able to make this proof work in very special cases, but in general, there were just terrible singularities which developed under his Ricci flow, and he certainly was not able to deal with this. So the final breakthrough came early in this century with the work of Grisha Perelman, who managed to find very surprising techniques for eliminating all of these, understanding what happened in each of these singularities. So the singularities which develop in the Ricci flow to a large extent corresponded precisely to the process which Thurston had described of cutting a manifold up into pieces, each of which has a good geometric structure. So finally, after 100 years, one had solved the complete generalized Poincare hypothesis. Well, what I want to go onto now is to ask what happens if we, instead of just looking at raw topology, we look at a smooth structure. And the point is, I quoted the original question of Poincare precisely because I wanted to emphasize that it's not totally clear what he meant. There were people he had studied smooth manifolds, topological manifolds. The terminology hadn't become fixed yet, so one could really interpret his original question in other ways. And if we ask for a smooth manifold, a manifold which is differentiable, we can ask whether it's diffeomorphic to the standard sphere. That is, whether we can find a homeomorphism which is smooth and has, I'm using smooth as a synonym for differentiable. If there's a homeomorphism which is smooth and has a smooth inverse. Well, you might try to proceed as follows. Given any homeomorphism between a manifold, a smooth manifold and a sphere, you can uniformly approximate it by a smooth map. This is essentially the Weierstrass approximation theorem, where it follows easily from it. So you might think it should just be easy if you can approximate the forward map by a smooth map and the backward map by a smooth map. You should be able to somehow do the two of them together and get a diffeomorphism. But this doesn't work. So you can ask whether this happens, but the answer is no. So at this point, I want to go to a more personal history. And in the middle 1950s, I was completely stunned when I found what seemed to be a contradiction in mathematics. I was looking at particular examples of namely three-sphere bundles over the four-sphere. These are objects which are very well understood, classified. They're manifolds, smooth manifolds. You can write out explicit formulas for each one is covered by two coordinate neighborhoods with very explicit smooth coordinate changes. So I was very put out when I looked at some of these examples. Oh, this is just, I can't draw you a picture of a three-sphere bundle over the four-sphere, so I compromised and drew a picture of a zero-sphere bundle over the one-sphere. You see, by a bundle, we mean we have a total space projecting down to a base space, and the pre-image of any point is the fiber. So in this case, the base space is a standard circle. The total space is a smooth circle, a twofold covering of it. And the pre-image of any point in the base space is two distinct points, which you can think of as a zero-dimensional sphere. So all you have to do is look at that picture and add a few dimensions, and you understand what I'm talking about. So I found examples where this total space M7 was a sphere according to a topological argument, but was not a sphere according to a different argument which used derivatives. And this just didn't seem to make sense. I didn't know what was wrong, but after analyzing the argument, the only way to get out of it was to assume that this object, this M7, was homeomorphic under a continuous one-to-one mapping to the standard sphere, but not diffeomorphic. This homeomorphism could not be made smooth with smooth inverse. So I want to get more technical for a little while, describing how one understands such an example. So first thing we need a method for proving an object like this is proving that a homeomorphism exists. But we also need a method for proving that a diffeomorphism cannot exist. So we have to prove things in two directions. And well, for proving homeomorphism, since the Poincare hypothesis is known, we now know that it's fairly simple to check. But this was before the proof. But there was still a very simple method which works in many special cases. So here's an argument due to Georges Rabe. What he considered a manifold and a mapping from the manifold to a line which had just two critical points. So there are just two points at which the derivative is zero. A maximum point and a minimum point, and he also assumed that some non-degeneracy of second derivatives, which isn't really essential, but makes the proof easier. So if you assume this, then you can see that a neighborhood of the, well, in any case, the neighborhood of the south pole is a nice disk, the neighborhood of the north pole, the maximum point is a nice disk, and you can just follow the gradient flow from one to the other and construct an explicit homeomorphism between this object and a standard sphere. In fact, if you're not very careful, you may think you've constructed a diffeomorphism, but you can make this construction into a diffeomorphism except at one point. So you can start with a disk at the south pole and just slide it up, and you can cover the entire sphere except for the north pole by show that it's smoothly isomorphic at the complement of a point in the standard sphere. But at that last point, you get stuck. Things have gotten may get very twisted. So that is the criterion which worked in these very explicit seven-dimensional examples. One had explicit coordinate systems, explicit formulas, and could work out such a smooth function in a very explicit way. But now let me go on to the other step, proving that the object is not diffeomorphic to a standard sphere. Here, the argument is much more complicated, and so the problem is to consider the certain explicit three-sphere bundles over the four-sphere and show that they're not diffeomorphic to a standard S7. And the proof will be based on a rather weird formula which connects three different integer invariants for a smooth eight-dimensional manifold. So to show how the proof works, I have to answer three questions. I have to, first of all, describe what are these three integer invariants. Second, how does one prove this integral relation between them? And finally, what does this have to do with seven-dimensional manifolds? This is a formula for eight-dimensional manifolds. So I want to take a few minutes to answer these three questions. So first of all, the invariant sigma of M4K is rather simple to describe. Go ahead. So for any oriented 4K dimensional manifold, closed, oriented, we can form the quadratic form. We take the middle dimensional cohomology and the cup product with itself, just as we did in the four-dimensional case. Now there's a slight complication here. There may be some torsion in the middle cohomology, but if so, we just ignore it. Some elements of finite order, that is. We just throw away elements of finite order, and then we get a quadratic form going from a free abelian group to the integers. Well, here I've used cohomology with integer coefficients, but we could just as well use cohomology with real coefficients or just tensor the whole quadratic form with the real numbers. And then any quadratic form over the real numbers can be diagonalized. We diagonalize it, count the number of positive entries, subtract the number of negative entries, and call that the signature. So that is the definition of this invariant sigma. Now, so what I need now is a formula which expresses this signature in terms of other invariants, which are called Pontryagin numbers, and the definition is a little bit more complicated and will require several steps. So let me go ahead. First of all, I need some classical constructions. Hassler-Whitney is perhaps the first big name in the field of differential topology. He's a founder of the subject. He made a clear definition of what a smooth manifold is, and he proved the theorem I'm using here, that any smooth manifold can be smoothly embedded in some Euclidean space if the dimension is high enough. And he proved that the dimension is essentially unique if the dimension is at least 2n plus 1. That is, if you have any two embeddings, you can slowly deform one to the other without ever introducing any kind of singularity. And now going back to the 19th century, Herman Grassman studied the manifold consisting of all n-dimensional planes through the origin in some specific Euclidean space of higher dimension. And I'll be interested in the case where L is large, because in order to apply Whitney's theorem, I need to embed in a large dimension. And since I don't really care about which large dimension, we can get rid of irrelevant details by passing to the limit as L goes to infinity. So each Grassmann manifold, take the Grassmann manifold of subsets of n plus one dimensional space embedded in the Grassmann manifold of linear planes through the origin in n plus 2 space and so on, and just take the union with a suitable topology, and I'll call that the infinite dimensional Grassmannian G sub n. Okay. Now I want to go back even further to Gauss, who studied what I'll call, studied for surfaces in 3 space, a construction which I'll use in higher dimensions. So if we have an n-dimensional manifold smoothly embedded in RL, then at each point x, it has a tangent n-dimensional plane. And we just translate that n-dimensional plane to the origin and call that g of x. So it's a mapping from the manifold to the Grassmann manifold of n planes through the origin. And then we just embed the RL into an infinite dimensional Euclidean space, if you like, and have the corresponding map. So now we have a construction that given any, given any smooth, closed, oriented n-dimensional manifold, we can, first of all, we have a top-dimensional homology class, which is canonically defined. If you think of cutting the manifold up into n-dimensional simplexes and just taking the sum of these simplexes, keeping track of orientations, we'll get an n-dimensional cycle, which represents the fundamental, what's called the fundamental homology class of the manifold. And now we apply this Gauss map, which takes the manifold to G sub n, and that induces a homology isomorphism from Hn of the manifold to Hn of G sub n. And this gives us a homology class in G sub n. So to any smooth, closed-oriented n-dimensional manifold, we get a canonical homology class, characteristic homology class in the Grassmannian G sub n. Okay, now let me pass to the work of René Thom. He was, I think, the second founder of the field of differential topology. He had marvelous intuition on how to combine geometric constructions with hard algebraic topology computations, and so as to answer geometric questions. And in particular, he asked this question. Suppose we're given a manifold Mn, a closed manifold, oriented. Can we find an n plus 1 dimensional manifold with boundary which has precisely M sub n as a boundary? And he was able to answer this question to almost answer this question. Well, let me give the theorem. The theorem that we can state is that a manifold is a boundary if and only if this characteristic homology class, which I've just defined, is 0. Well, he didn't quite prove this. What he was able to prove was that that this is true up to elements of finite order. Let me just go ahead and so the point is that this well, he proved it up to elements of finite order. Then Terry Wall carried out the proof to understand the two primary component. And Sergei Novikov and myself and I took care of the elements of odd order. So I've just stated the theorem in this simpler form, precise form, not because I need it, but for the purpose, but I think it's a cleaner statement, easier to understand. So let me go ahead. Now, Tom further defined this concept of cobordism. So given two different closed-oriented manifolds, M1 and M2, he asked whether they could be joined by a n+1 dimensional manifold with boundary in a way compatible with the boundary so that you obtain a well-behaved equivalence relationship. And he showed that the equivalence classes, the cobordism classes, formed a group where the sum operation is just taking disjoint union. So if you take two manifolds and put one of them here and one of them here and take the union, that's another manifold which is not connected, but that one can ask whether that manifold is a boundary, and in this way you form an abelian group, because clearly the disjoint union is a commutative operation. You don't care what order you take them in. So we can restate the theorem before in terms of this cobordism relation. We map the cobordism class of M to the fundamental homology class of M, and the theorem is that this embeds the cobordism group as a subgroup of finite index in the homology of the Grassmannian. Now, I have to proceed further with this. I have to define Pontryagin numbers. These were introduced back in the 40s by Lev Pontryagin. I think believe the cohomology terminology perhaps wasn't available or wasn't known to him, but we would now state what he did by saying that he defined certain cohomology classes for the Grassmannian, but only in dimensions divisible by 4. And he showed that if you ignore elements of finite order, then these generate the cohomology ring. So every cohomology class can be expressed as a sum of products of Pontryagin classes, where product always means cup product. So in particular, the cohomology group H8 of G8 is generated by two elements. You just look at what products of Pontryagin classes have dimensions adding up to 8. You can take P1 squared or P2, and there are no other possibilities. So now, if we have a manifold, a smooth manifold, then we can evaluate these two cohomology classes in dimension 8 on the 8-dimensional fundamental homology class, and that gives us an integer. So that gives us that. I finally defined these two Pontryagin numbers. They're obtained by evaluating these two Pontryagin cohomology classes on the fundamental homology class of the manifold. So I've finally answered my first question. What are these three integer invariants which I want to work with? So now I have to ask the next question: how could one prove a relationship between them? And this was done by René Thom. So he proved that by a simple geometric argument, that if a manifold is a boundary, then its signature is 0. And so and then it followed that if two manifolds are cobordant, then they have the same signature. And this gave us a homomorphism from the cobordism ring, or from the cobordism group, rather, to the integers. And then, since he knew the cobordism group up to elements of finite order, it followed as a corollary that the signature can be expressed as a linear combination of Pontryagin numbers. But the startling fact was that even though this is a relation between a number of integers, 3 integers in the 8-dimensional case, the coefficients that expressed one thing in terms of another were not integers, they were rational numbers. So that here's an explicit formulation in general. The signature can always be expressed as a linear combination of Pontryagin numbers where the a's are rational coefficients, and we're summing over all combination products of Pontryagin classes which have total dimension equal to the correct dimension, 4K. Well, Tom was able to give explicit examples in low dimensions, but then about the same time, Brook made a complete computation of what all of these coefficients were. And this was a computation in terms of Bernoulli numbers. So now we're skipping back 250 years to Bernoulli, who worked around the year 1700. Well, I mention this not because I need it for the 7-dimensional example, but when we're studying higher dimensional examples, the number theory of the Bernoulli numbers plays a very important role, not only for studying differentiable spheres, but also for studying homotopy groups of spheres. So this was an amazing connection between number theory and topology. Go ahead. Okay, so I've answered my first 2 questions. I've described what these 3 integer invariants are, and I've described how one finds a relation between them. But now I need to say, what does this have to do with 7-dimensional manifolds? So we ask the following question. Instead of dimensions 7 and 8, I will work with dimensions n and n-1, but the construction will be the same in all cases. So go ahead. Suppose that we're given an n-dimensional manifold which is bounded by a topological sphere. So I'll assume I have a smooth manifold and, well, I don't need a smooth, I'm sorry, what do I need? If we just have a topological manifold with this boundary as a topological sphere, we can paste a disk onto the end. The boundary of our manifold En is the same as the boundary of the standard disk Dn, and we just paste the boundary on and we get a closed topological manifold. But now suppose that En is a smooth manifold and that this correspondence between boundaries is a diffeomorphism. Then we can easily smooth out the differentiable structures and conclude that the manifold we construct actually has a differentiable structure. So this is the the way that dimensions 7 and 8 are related. Suppose that this, so we have a certain 7-dimensional manifold which we want to study. We can show that it's a boundary in a natural way, because if you have a sphere bundle, it's just the boundary of a disk bundle. That's an immediate construction. So the manifolds we're interested in are boundaries in a natural way, and if we want to ask whether the boundary is a smooth sphere, we just paste a disk on and ask if this resulting 8-dimensional manifold can exist. So let's go ahead. I consider the 8-dimensional case, and we can now let's look at these 3 integer invariants. The signature is a cohomology invariant which can easily be computed if you understand the cohomology of the pair, the manifold E8 together with its boundary. And similarly, the Pontryagin number P1 squared M8 can be computed if you know the structure of E8 is a smooth manifold. Now the top Pontryagin class P2 of M8 is not so easy because its definition involves the whole manifold in an essential way. But we can use this integer relation, which takes this form. So we know how to compute the two integers on the right, and we can compute this combination. And it turns out that in the cases I was looking at, this quotient was not an integer. It had a denominator of 7. And this proved that the boundary could not be diffeomorphic to the standard sphere. So this completes an outline of how this example appeared. Well, now I want to describe a little about what happens in other dimensions. So let me go ahead and first of all describe a simple way of putting manifolds together in any dimension. So suppose that we have two oriented connected manifolds of the same dimension. Then the connected sum is a new smooth oriented connected manifold. And the construction is the following. Here are two manifolds that we want to add. We embed a standard closed disk in each one. So in any manifold, you have a smooth manifold. You can embed smooth disks easily. And you cut out the interiors of these disks and paste the boundaries together according to the canonical homomorphism between their boundaries, being very careful with orientations. And that will give you a new manifold, which we can visualize in this way. If we think of them as being next to each other in Euclidean space, then we just push them together, glue edges together, and get a figure like that. Well, this is easily seen to be a commutative, well-defined, first of all. There's essentially only one way of embedding a smooth manifold one way of embedding a standard disk into a smooth manifold up to a smooth isotopy. So it's well-defined, and it's commutative and associative. So we get a semigroup, or a monoid if you prefer. It's a semigroup which has the sphere as identity element. If we take this, add a sphere to any manifold, we get something which is diffeomorphic to the original. So we get a nice semigroup, which, well, this is most familiar in dimension 2. If we take the possible smooth closed surfaces or just form a semigroup on one generator, the torus. If we add a torus to itself, we get a surface of genus 2 and so on. In dimension 3, you have a similar decomposition into primes, although now there are infinitely many prime manifolds. By the time you get to 4, it gets more complicated, and you don't even have the cancellation property. But it's a well-defined monoid in any dimension. And now I want to ask the following question. Can it happen that a manifold is invertible in this operation? So given a smooth-oriented manifold Mn, can we find another manifold n sub n super n such that the connected sum is isomorphic to the standard sphere? Well, this question was answered by Barry Mazur back in the days before he became an algebraist, or a number theorist, whichever you describe him as. He gave a very simple criterion. The manifold is invertible if and only if it becomes diffeomorphic to, if and only if you remove a point, you get the same thing you would get if you remove a point from the standard sphere. Namely, you get something diffeomorphic to the standard Euclidean space. And let me give the proof in the hard direction. Oh, I'm sorry, this is the natural consequence. If removing a point you get Euclidean space, then clearly the thing is topologically a sphere, because if you take the standard Euclidean space and add a point at infinity, you get a sphere. So I'll give a proof in the hard direction, proof that the first property, invertibility, implies the second, that if we remove a single point, we get Euclidean space up to diffeomorphism. And the proof will involve the idea of an infinite connected sum. So as an example, suppose we just take an infinite sequence of copies of the standard sphere and add them all together. I claim that the result will always be Euclidean space. So here's a picture illustrating the one-dimensional case. We take a row of circles, join them together in pairs, and you've got an object like this, and you can clearly sort of pull one end up and one end down and straighten it out to be a real line. Or if you take this figure and rotate it around the x-axis, you get a similar picture where you can, for the two-dimensional case, where you clearly can straighten things out and get a two-dimensional plane. And the argument in n dimensions is essentially the same, just rotating through more dimensions. So now let me prove that 1 implies 2. So we start with an alternating sum. I'm assuming that m plus n is isomorphic to a sphere, and I take the alternating sum m plus n plus m plus n, and so on. And if we put in parentheses one way, then we get sum of spheres, which we've just seen is diffeomorphic to Euclidean space. But we can also put in parentheses in a different way. We can take m and then add n plus m and n plus m, and so on. So in this case, we get m plus Rn. Well, Rn you can think of as a sphere with a point removed from the point of differential topology. And the sphere is the identity element. So this is just the same as taking m and removing a point. Let's see, can we? Yeah, thank you. So this completes the proof that 1 implies 2. We just started by assuming we had an inverse and conclude that m minus a point is diffeomorphic to Rn. Well, I won't get, let me leave the proof that 2 implies 1 as an exercise. It really just follows from the definitions if you do a little work to see what the definitions mean. And we already pointed out that 2 implies 3, so this proves the lemma. Well, this then gives us, it shows that if we can find such manifolds, such that m minus a point is Euclidean space, then we've found invertible elements in this monoid. Well, more generally, let me describe work now with Michel Kerver. We considered this, well, I'm simplifying here a little bit. What we actually considered was homotopy spheres up to an operation called H-cobordism. But given the work of Smale, we know that homotopy, or given the generalized Poincare hypothesis, we know that homotopy spheres are the same as topological spheres in most dimensions, and the H-cobordism theorem says that H-cobordism theorem says that H-cobordism is the same as diffeomorphism in most dimensions, in high dimensions. So it's a little bit more natural just to look at this semi-group of smooth manifolds which are homeomorphic to the sphere under this connected sum operation. Well, for dimensions 1 and 2, we clearly get there's clearly nothing happening. We could just get the trivial semigroup. For S3, certainly Michel and I were not able to handle it, but now in view of Perelman's theorem, we know that this is trivial. And we were able to handle the case of high dimensions, of dimension 5 or more. We proved that this is always a finite abelian group. So there are always inverses, so all of these manifolds have the property that if we remove a single point, we get the standard Euclidean space. Or to put it another way, they're diffeomorphic to the standard sphere, except that the differentiable structure may be messed up at one single point. And so the next two cases, S5 and S6, are also trivial. Nothing interesting happens. But then the 7-dimensional case, which I've just described, it turned out that the group is actually cyclic of order 28. And we were able to work out other cases. The next case, cyclic of order 2. The next case, I think we were only able to prove that it had order 8, but we now know that it's a direct sum of 3 cyclic groups of order 2, and so on for suddenly at dimension 11, and it gets bigger again. This is somehow the large denominator is connected with the denominator of the Bernoulli number. 12, it gets to be 0 again. So again, the differentiable Poincare hypothesis is true in dimension 12 again, although it's false in dimensions 7, 8, 9, 10, 11, and so on. So we developed a method of analyzing these groups by using geometric arguments to reduce the problem of classifying differentiable structures up into problems involving stable homotopy groups of spheres and stable homotopy groups of rotation groups. So certainly can't give the details here, but let me just first of all say what some of the ingredients are. So higher homotopy groups were introduced by Hurevich, but he wasn't able to say much about them. He proved that they had nice properties, but nobody knew really what they were. Then the first really constructive work was in the thesis of Jean-Pierre Serre, who developed a very elaborate algebraic machinery for analyzing such groups. And these spectral sequence methods, which he introduced into topology, have been a basis for all subsequent work in the subject. And then but this is still a sticking point because it's a complicated construction, and people have worked out the homotopy groups of spheres up to a point, but don't really know all of them. On the other hand, Raoul Bat, studying stable rotation groups of rotation groups, was able to get a complete answer by a beautiful geometric argument. So these were the ingredients which Cavere and I were able to apply. We didn't carry on. We started to describe how to attack the problem, but didn't try to proceed into more computations. But many other people have carried on the work. So let me just go through them rapidly. Frank Adams made very important contributions very early on. Greg Brumfield showed how that many of group extensions which we'd described were always split. So they just had a direct sum. Bill Browder made the beginnings of an analysis of what's called the Kervère invariant problem, understanding a certain homomorphism from homotopy groups of spheres to the integers mod 2, which is tied up with these exotic spheres. And Mark Mahowald carried computations much further. And the most recent development, just in the last year or so, is by Hill, Ravenel, and Mike Hopkins, who is here today. Well, I'm running out of time and can't say more about this. But with all this work, this group of this monoid, rather, of essentially monoid of differentiable structures on spheres is known up through dimension 64 now. After that, one doesn't know the stable homotopy groups of spheres well enough to give a precise answer. But there's one exception. Remember, we could handle low-dimensional cases by geometric arguments and high-dimensional cases by spectral sequence arguments and so on. But somehow nothing works in dimension n equals 4. The dimension isn't large enough for general position arguments, which are very important here to work. So let me just very quickly say something about this last case. So what we do know about smooth manifolds in dimension 4 comes from a surprising source, from methods developed for mathematical physics in gauge theory. And Simon Donaldson was the first to bring in these methods, and he proved a theorem which we can state as follows. Suppose we have a smooth, simply connected 4-manifold with positive, definite quadratic form. Then it can be diagonalized, not just over the real numbers, but over the integers. And in view of Friedman's theorem, this means that it's homomorphic to a connected sum of complex projective planes. But on the other hand, there are many unimodular quadratic forms which cannot be diagonalized. So there are many, many examples of 4-dimensional manifolds which cannot be given any smooth structure. And somehow the results of Friedman and the results of Donaldson were just totally incompatible, so that if you make use of both methods together, you get rather amazing consequences. And again, I'm running out of time, so let me just state these quickly. So Friedman and John Morgan showed that a closed topological 4-manifold can have infinitely many essentially distinct differentiable structures. In fact, they studied specific examples, K3 surfaces, and showed that in that case there were infinitely many essentially distinct differentiable structures. Then Cliff Taubes looked at the simplest, perhaps what you might think of as the simplest case, just the 4-dimensional Euclidean space, and was able to show that that the R4 has uncountably many distinct differentiable structures. And by distinct, I mean that they're pairwise, not diffeomorphic to each other. So they're just an uncountable collection of smooth manifolds, all of which are topologically R4, but which differentiably are completely distinct from each other. And these things can happen only in dimension 4, because for n different from 4, there's a theorem that a topological manifold has only a finite number of structures up to diffeomorphism. And there's a theorem that the Euclidean space has a unique differentiable structure up to diffeomorphism. Now, these last two statements, I can't state one author, one person who's proved them, because they come by combining results from many different people. But these are well known. So finally, let me go to what can we say about this semigroup of differentiable structures on the 4-sphere? Well, what is known? It's certainly a commutative associative semigroup with unit, since it's a subgroup of the commutative associative semigroup of all smooth 4-manifolds. And it has at most countably many elements, and any compact manifold has at most countably many differentiable structures by a simple argument. What isn't known? Well, everything else. So is it a trivial group? Or is it a trivial monoid, rather? Is it finite? Is it finitely generated? Is it a group? No one knows. So just let me, in the last slide, I'll just give you a few references where you can find some more details about these things, but I'd better stop now.